He joined University of Albany, the research center. When physically you moved to Albany?
In August.
In August. So
last year.
He is in the process of getting his official title. He will be a research scientist, research faculty at the research center in Albany. I know Ivan from the days back in Houston during the Escape Research campaign. His PhD is from Colorado State University with Professor Chandra, where he learned radar. His background is on signal processing hardware, but also microphysics, extraction of information out of the radar signal. After his PhD in 2023, he did a short passage through the Naval Postgraduate School in Monterey, working with Scott Power. And as we heard, he is now in Albany. He is very dynamic and ambitious. He wants to build his own radar program, which is great for the state. So he's here to talk to us about some of the work that I assume you did during your PhD on microphysical retrievals from multiple radar observations during the CACTI and RELAMPAGO experiments in one of the places where we have the strongest inland convection in Argentina.
Yeah, well, thanks for the thanks for the invitation. And yeah, as you mentioned, like I just moved recently to Albany, to the state, and I'm working at the Atmospheric Science Research Center, so research faculty, and these are like some of the work that I did in Argentina. So I was in Argentina for this field campaign and collecting data. That's what I'm going to show today. So these are some outlines for the talk. I guess these two radars, like I guess the CSU Chivo radar is the radar that I deploy in Argentina, and I was collecting data there like for the full campaign. Almost like I was there almost like 3 months, and I'm also using the CSAPER radar, which is a radar from the Department of Energy and the ARM facility. So I'm doing like multiple radar kind of like observations and some of the retrievals that I'm going to show today are from these two radars, but I also included other radars that were deployed during this campaign in Argentina. And what the work that I do is more like using multiple radar observations. So basically, when you have like a multiple radar observations, like you are taking observations from different angles of the storm, and that allow you to do more advanced retrievals. Like you can do a Doppler retrieval, so analyze, in this case, more like the microphysics, like depending on the path that each radar kind of like the signal goes, it's exposed to different kind of like attenuation. So that's one of the things that I do. And I will show today more like a network attenuation correction, which is an approach like once you have multiple radars, then you try to combine all the radars and find reflectivity or radar moments that match the best, kind of like reconcile the whole network of radars, and that provide kind of like radar moments that will have higher data quality than if you do it with a single radar. And also, you can retrieve the W using like Doppler analysis. So there are many advantages of using like multiple radars observations. These are more like a background slide, so you're probably familiar with this about what the radar measure is. It's more like a distributed target where you actually what you get is like a bunch of backscatter from each drops that are in the clouds, and that's what the radar measure. So and then if you apply some like some scattering theory, you can derive what is called the reflectivity, which is basically backscatter. But then since it's a distributed target, you end up getting like I forget 6 here, but basically the 6th moment of the drop side distribution is what you get in your reflectivity equation, and that's proportional to the and then depending on the wavelength, I guess. So basically the radar is more sensitive when you have a smaller wavelength. guess I'm out of this here, but yeah. So yeah, and then when you do like dual polarization, then you transmit a pulse in the vertical and the horizontal, and then you can know more about the shape of the particles, and then you can retrieve like hygrometer classification or understand like what are actually the type of particles that you are measuring, and it helps you to understand more about the microphysics and what's kind of like processes that are going into the cloud or the storm. And then yeah, so we have the differential reflectivity, which is the ratio between the horizontal and the vertical, and then the differential phase, which is like the shift in the phase that the vertical and the horizontal receive, and then we have when you measure the reflectivity that you get is attenuated. Normally, if you are in a C band or an X band, and then we use PDD to correct for attenuation using some coefficients, which are going to be important for later when we have like enhanced attenuation, like when we have melting ice. These coefficients have to be adjusted if you want to account for this attenuation. But yeah, I guess just keep in mind like there are some ways to correct for the attenuation using PDD, and then this coefficient alpha, which is account for the attenuation. Yeah. So then another variable that I'm going to be using in today's talk is the Doppler velocity, and then basically Doppler velocity is like when you transmit a pulse, if there is any movement with respect to the radar, then you will have a displacement in the frequency due to the Doppler effects, and then this is proportional to the frequency displacement, or the Doppler velocity is proportional to the frequency displacement, and then it's negative. So basically, negative velocity means like going towards the radar, and positive velocity is away to the radar, and it depends on the wavelength. So when you don't have like particles are not moving, this is more like the spectrum that you will observe, like based on your time series. And then when there is like turbulence on the measurements, then the spectrum will look like kind of like depending where things are moving, it will look more like to a spectrum that is on the right. Yeah, so keep that in mind. So yeah, and then the data set that I will be using today come from these experiments, the CACTI and RELAMPAGO experiments. And some of the reason we send radars to Argentina is because this is one of the hotspots of like convection in the world. So this map shows like where the tallest storms are using TREE, which was a satellite climatology. So basically, you see like there's a hotspot here in Argentina. There's another in the Great Plains, and in Africa, this part in the Himalayas. So we send these radars to Argentina to study this tall convection, and also because it's very frequent to have convection there. So it was more like a natural laboratory to study convection, because it's like really tall storms, very frequent, and that produced tons of hail. And so yeah, and we sent this radar from Colorado State University, the CSU Chivo radar, C-band radar, and yeah, you can see here like some of the storm reaches like almost 20. This was an RHI, which is a vertical cross section. You can see like some of the storm reaches almost like 20 kilometers, and this is above ground level, and the radar was sitting like probably 400 meters high, so it's probably higher than like the Echo Tower, probably higher than 20 kilometers, which is a pretty tall storm considering like normally flights like airplanes goes normally at 10 kilometers high, so it's one of those kind of like really tall storms, and there was a tons of hail reported too. So yeah, and then we have measurement from these two radars, and also a radar that I won't show before that I use in my analysis. So So yeah, these are the radars that were deployed in Argentina. So we have the Chivo radar, the Sea Sapper, the C-band wheel radar from the farm. And then the operational radar was also a C-band radar. So all of them were C-band radar with similar characteristics. And this is the topology where they were deployed. And you can see like the baseline between them is still good enough that we could produce Doppler wings for each kind of like pair of radar. And most of the storm kind of developed like on the eastern slope. These are the sierras de Cordova where kind of serve like a lift mechanism, kind of convection initiation, and then from there they grow into really massive storms. So yeah, so these are the topography and the baseline of the radars, and we were able like to conduct Doppler winds. And this is one case just to show like that I'm gonna be referring about this case. Was in December 14. So we got a cold front, and then cold front kind of interacts with the terrain, and then the cold front interacts with the rain, and then boom, produce like a really heavy precipitation with tons of hail later on. And then you can see how the cold front advances with the Doppler velocity. And again, like negative velocity is towards the radar, and once it passes around 130 UTC, it is where this massive event happened in this domain. So this is after the cold front passes, and then I conducted some Doppler winds using the radars that I showed you before, and you could see like, I guess this is the front here, and then you see like some convection initiation in this part start happening behind the front, and then I retrieved like different like, so basically for each pair of radar I conducted Doppler winds, which is like basically reconstructed the 3D winds using two radars, and then you could see like this wind matches, and then when you average them, is to have like a more complete map of the winds. Then you could see more like a complete map of the Doppler analysis, and then you could see a convergence along the boundary here, and I threshold these to like remove some clutter, but basically where you don't see kind of like echoes is where I was using like no meteorological echoes to reconstruct the Doppler winds before initiation. So that's what they are. But those non-meteorological echoes help you to figure out what was going on previous convection initiation. So I leave them there and still run the Doppler analysis on them. Yeah, and then 10 minutes later, you could see like this system start kind of like evolving or kind of like organizing into a squad line, and you could see like at the low level you have kind of like southerly winds, and then they shift. There is a strong shear happening, and then you see this shift in shear at 4 kilometers captured by the Doppler analysis. And you see the radio sounding that was taken on the sea upper side at the AMF. That we had similar pattern, like at the low level we have kind of like southerly winds that later shift to into like these kind of like diagonal winds here. So we have confidence that we did a good job reconstructing the 3D or the horizontal winds for this case. And this is the trajectory of the radiosondes here. So we reconstruct these 3D winds. This is another case that I analyzed for the Relampago campaign. That was on the January 25th, and you could see here there was a picture that was taken, kind of like it was a supercell that was splitting, and then this is like a kind of like a rotation of the image using the Chivo radar, and you could see the two towers there and the anvil here that is kind of developing. So I also did like Doppler winds on that case and check how the data looks like for the Doppler winds retrievals. And this is how it looks like on the vertical. So basically, I use for this Doppler analysis, I use GEO and C-Zapper radars to reconstruct the 3D winds. And you could see here, there is some recirculation pattern where the high reflectivity values are, which is probably associated with hail growing. And also, I don't know if it's easy to see, maybe not, but there is like some vorticity here that were captured also by the Doppler winds. So yeah, we have tons of cases like this during the Relámpago, and it was like not only like a couple of cases, but I think we got like 30 days with convection that the radars were operating. Was pretty like remarkable for a field experiment to have like 30 IOPs with deep convection in it. So I ran this systematic Doppler winds analysis during all these 30 cases in Relámpago, and then analyze some of the statistics of them. And that's some of the work that I'm showing today. So it's basically 3 months of radar data, and we have like 30 days during these 3 months that we have deep convection, and so I'd say 20, but we actually analyzed 30 days, and then we analyzed how the updraft and downdraft, and this was some of the work that I did during my postdoc in the Naval Postgraduate School. We analyzed how the updraft and downdraft distribute during these 30 days, and for that we use this. We use only convective cells. So we use a previous data set that was developed for the CACTI experiments that kind of like track cells. So we use that data set to isolate cells where we have convection, and then we analyze those. And these are some of the distributions. So we have similar distribution. I guess updraft were a little bit higher because we were analyzing only convective cells. So it makes sense to have maybe updrafts to be a little bit higher. But they show like a distribution that are what we kind of expect from our work. And this data set is available if anyone wanna work with it. It's in the ARM data archive. It's public.
When you show the updraft, is the updraft the space between the downdraft and the top of the updraft, or is it from the top of the updraft all the way down to the x-axis?
Yeah, it's all the way down. Yes. Yeah. Okay. So updraft. So what this plot means is that updraft counts were higher than downdraft counts.
Got it. Thank you.
Yes. Yeah. Good question. And same for the velocity. So basically, updraft velocity in this case has to be higher than downdraft velocity. So we also compute like the distribution of these updrafts at different heights, and we put in a logarithmic scale. So basically, basically like 30 dBc here means like 1,000 counts, and that's what. And then we didn't took into consideration like low kind of like velocities like between plus and minus 1 meters per second in the analysis that I'm gonna show later, just because there was like more uncertainty there that it was actually an updraft or a downdraft, and these are the distribution of the downdraft and updraft at different heights, and then you could see like probably you have more like a high values kind of like happening between 8 and or a peak, and then this dotted line is the average of the downdraft to the left and updraft to the right, and then we can see we have like higher or like a peak between 8 and 10 kilometers, which where the updraft peaked in this case. So and then we also analyze the different like distribution at different heights, and then we found like the reflectivity or the differential reflectivity has more like diversity at the low levels, which probably makes sense because that's where things are melting, and then we probably have more like higher reflectivity. One thing to mention is like I also corrected for attenuation correction for this event. So so it's this differential reflectivity is attenuation with attenuation correction reflectivity too. So that's why you see like probably like differential reflectivity is higher than 0 at the low levels, and then we're getting closer to 0 that you see when you were up there in the atmosphere. And then similar for KDP, we have like kind of like more diversity at the low levels because things are melting, we have more water content. And then at the upper levels, it's sort of more like centered to the right of 0 degree per kilometer. So yeah, but I think like we did this for updraft and downdraft, and then to see the difference, we took like what I call was more like a differential ratio between updraft and downdraft distributions. That is basically this plot that I'm showing here. So I took the probability from updraft and then divided over the probability of downdraft at each specific measurement and each specific height. So and then I put it in a dB scale because I'm a radar person. I like dBs, and that's that's the way. And it has its advantage because it's a ratio. Then when you put it into dB, it's actually a difference. So if you see positive values, means that the probability of updraft is higher at one particular height and one particular radar measurements. And if it's negative, then means like the probability of downdraft is higher. So it's also intuitive to look at it. And that's what I'm showing in this plot here. It's the distribution of reflectivity and height. And then the X means like the probabilities are statistically significant. So you could see, for example, for that the updraft kind of like dominates this region here at the low levels and with low values of reflectivity, which I think could indicate like maybe having like updraft kind of like preventing kind of like precipitation to fall and having some of the like these weak ecoregions that the updrafts can produce. And then when we have more like heavy precipitation, that's when we're probably having like higher values of reflectivity at the low levels. And that's probably why we're having this region here dominated by downdraft. And then we have this region here, which is like high values of reflectivity and high values of and at the upper level. So we think that's probably produced by health that is sustained by updraft at these higher levels. And then I also found like what was the most prevalent hydrometric classification both for updraft and downdraft. And then that's what I'm showing here. So and then we found like for this region here, we found like this light blue here is what this is health when the hydrometric classification from the radars is all health. So it's kind of consistent with this. And similarly for the differential reflectivity, we have kind of like this area of high of positive CDR happening for updraft, which could be related with CDR columns. And then when we have precipitation, we have probably more of late kind of like precipitation falling. We have more of late particles, which that's probably why we're having more like dominated by downdrafts here. So yeah, this is kind of like the statistical analysis. Yeah, so and that was like a way to visualize like, okay, what's going on, why is this each region is dominated here by updraft or downdraft, what kind of particles can be there, and these are like again all these rare like Doppler winds analysis are in a database that is publicly available if anyone is interested in taking a look at. So yeah, and then another study that I've been doing is accounting for the attenuation of melting ice, because using this data set in Argentina, because we have tons of ice, like tons of hail recorded on the ground, and this is for one of the cases that I was showing before, the December 13, December 14, 2018 case. In that case, we have tons of like hail reported on the ground, and since we have like multiple radar observations, and the attenuation of melting ice is still one of like an active area of research in radar meteorology for short wavelength radar like C-band, X-band, because we have like a mean scattering there and resonance. So I use this data set to account for the attenuation from observations of melting ice. Then I use the network-based approach, basically using these two radars, the CSAPR and the Chivo, and then I use the storms. Like on Doppler widths, we try to avoid the baseline, but in this attenuation study, I actually tried to focus on the data that was in between the two radars. Like once the two radars measure the same storm, then I was trying to come up with a reflectivity that was matching both the radar in the best way. So this is a plot of the differential reflectivity taken at that case, and again, that case we observe tons of hail on the ground. So this is the differential reflectivity from both radars, and again, both radars are like the radars are looking at the storm at different angles, and I'm just centering both plots at the Chivo location, but actually this is where CSAPR was, and this data from CSAPR just a different kind of like coordinate position. You could see here, we kind of go through this region here of positive CDR, and then we pass this region with kind of like enhanced values of differential reflectivity, and then after that we have negative CDR. But if we look at the same storm, same time from the Chivo radar, look at like the storm looks pretty much the same, like same structure, but it's the reflectivity, the differential reflectivity is kind of flipped here. Like we go through this region of positive CDR, something happened in this box here, and then we got negative CDR down the string of the beam. So we are thinking like, hey, something is happening here that is, and this is after attenuation correction. Something is happening here that my algorithm is not catching the attenuation in this part. So I was diagnosing this. This is an RHI that I took like right a minute before, like those PPIs that I was showing before, and you could see like at this RHI, you see like the storm is kind of like have like all these high values of reflectivity here, matching these kind of like enhanced values of differential reflectivity, and then we have these negative values that are already like the algorithm is not able like to catch up like the differential reflectivity. And when we run hyrometer classification for this case, based on these moments, then we have like this region here, which is what hyrometer classification is resulting as a mix of rain and hail in the pink colors here, surrounded by large drops. So we think like what we were having was actually melting ice in this region that was affecting the CDR to the point that was not able to catch up. Like the algorithm was not able like to correct for the differential reflectivity after passing this region of melting ice. So what I did was basically use this the network-based approach, basically finding like a reflectivity and a differential reflectivity that match both of the radars, and then find like which radar you trust more at a certain point than the other. Like if you don't have any storm and you're looking at if you don't have any weather in between and you're looking at the storm on the one edge, but the other radar has to go through the whole storm and looking at the same value, you probably trust more the radar that has a clear view to that point. So it's basically that's the concept behind this network-based approach. So you basically use the data that you trust the more at a certain point. or has more data quality. And these are like some profiles along the beam that I was showing that was having like some enhanced attenuation. And you could see, well, here the magenta is the measure reflectivity, and once you correct it using just regular attenuation correction is the red line here. And then the network-based approach is when you use both of the radar and using like the information from both radars to correct attenuation is the blue line, and you can see like the blue line, like the network basis, where the red line is not catching this, all like this portion after it's passing through this melting ice region. So what I did is like, well, we're pretty good catching like this until here. So if, like after that, we probably need to enhance the attenuation correction coefficients. That's what I did to kind of like make this now this magenta line is the enhanced attenuation using like increasing the attenuation correction coefficient in this portion of the storm that was having melting ice to catch up to these to the network base, which was my ground to match. And I did that for many cases, many beams, and I created like an statistics and for attenuation correction, and then these are the sizes that I found from the coefficients, and this problem has been studied in the past with simulations. So these are like the span of the attenuation correction coefficients for melting ice that has been found from simulations, and then these are the distribution that I got. That is kind of like in this range of that has been found in the simulations, and then similarly I did the same for differential reflectivity, and then my coefficients were a little bit higher, but still overlap what has been found. What has been found with simulations. So, and this is probably the first time this has been done from observations. Like this kind of study has been done for simulations before, but I guess since we have like tons of data from the Relámpago campaign to run this kind of statistical analysis for melting ice, and because we have like really high quality radar observations from both radars, we were able like to conduct this from observations. Yeah, objectively. Yeah. So yeah, yeah, I think it's so those are the two words that I wanted to show you today. And so yeah, in summary, we use multi-radar observations. So gives you more than just one radar observation. So when you have multiple radar, you can be more creative with the type of analysis you can conduct on the data, and just having like observing a storm from multiple views just gives you advantage of like knowing what's going on in the storm from different perspectives. That can let you also like get like more advanced retrievals like Doppler winds, and we conduct this Doppler winds analysis systematically for many cases, and yeah, this database is now publicly available if you want to take a look at like different. It's not only Doppler winds; it also has polarimetric data in the database like CDR, reflectivity, and rate speed. So you can know what kind of characteristics are happening in different kind of like environments, downdraft or updraft, and yeah. So what we found was like updraft tends to dominate, or we found like which regions tends to be dominated by different updraft or downdraft. One thing is like these are the falling or the final velocity that we are observing from the radars, like the 3D or the Doppler winds analysis actually gives you the final, or it gives you like the velocity of the gyrometers, but it doesn't give you like what's the velocity of the wind right there. So that's really some future work, like trying to remove that component and actually give you more of what's the winds kind of like happening. And yeah, then we use these simultaneous radar observations for studying the melting ice. But I guess there are multiple things that can be done with these simultaneous observations from multiple radars. And in this case, we have like 4 radars and tons of storm happening in between the 4 radar. And the 4 radars were a C-band, which it's nice that you have consistency between like the wavelength that you are measuring. So you should be measuring the same kind of radar variables, and if you're not, then something is going on. That's what I've been trying to figure out. In this case was melting ice, but yeah, it could be other microphysical, mixed phase, etc. Okay. So I guess yeah, that's my thanks.
Thank you, Ivan. Time for questions, Michael.
Yeah, you mentioned how deep this convection was. How able were the multiple radar systems to be able to scan through the entire volume of these storms?
Yeah.
Or was it just 1 or 2 or all of them?
Yeah, that's a yeah. Some of them didn't capture all the ecotopes, because you saw the ecotopes were sometimes like 20 kilometers or very like they were really tall storms. So sometimes we miss the ecotop for some of the storms.
So what's the impact of that vertical velocity?
Yeah, that's a good point. In that case, we use mass continuity to retrieve W. So basically at the ground, yeah, if you have convergence, you have to go up, and then at the top, when you have to measure the ecotop, and then if you're at the top, that's it. Like that should be like a 0 kind of boundary velocity. But if you don't capture the ecotop, then we're only using like the boundary at the ground. So it could add kind of like noise when you start going like when you start retrieving the velocity in the upper levels.
But it also introduces air.
Yeah.
Yeah, and what were the update times that you guys?
So we did it every 10 minutes. So each radar we're doing like different scan strategy. So basically, is that your question? Like how often?
Yeah.
Yeah. So yeah, each radar was doing different scan strategy. So Chivo was doing like every 10 minutes. Then C-Supper was doing every 15 minutes. Kind of like a volume scan. And the cow was doing its own thing, like whenever they were like in an asynchronous kind of a schedule, like whenever they finish and RHI they started a PPI, so it wasn't like that much synchronized. So I tried to do like an output every 10 minutes, basically using like Chivo to anchor like which other retrievals or which other radars were available when Chivo started like doing a volume scan. So yeah, in short, normally Chivo has like one of the radars that was synchronized well, like every 10 minutes.
Okay, so you're doing vertical velocity retrievals every 10 minutes.
Yeah.
So I think it's been shown that one of the biggest impacts on the validity of vertical velocity retrievals are those update times that you get above like 4 or 5 minutes and introduce error. So what kind of errors do you think you're dealing with? Combining those 2 ideas, what kind of errors do you think you're dealing with?
Yeah,
in your vertical velocity retrievals?
We try to stay. We produce every 10 minutes, but we use radars like that were less than 5 minutes, like taking data simultaneously at the same part in between these 5 minutes, kind of like boundary. But yeah, like those storms evolve really fast. Like you saw, like the storm that I was showing you, it was just blow up. And less than 20 minutes. It was just organizing itself. So this started really like fast evolving. So I think.
But do you think that there's the possibility of errors, Mr. Cables? Like what do you have in error bars?
Yeah, I don't have an error bars. I guess like the closer I get for an error bar was like getting like the retrievals for like when we have like like more than 3 radars were showing like radar at the same time. Like we got like retrievals from the 3 pairs of radars, and then we kind of observe like they kind of align, like the errors align kind of like at the same. But I think that could be a way to obtain, like if we like use different kind of like pair of radars to see if how well the velocities align between them. But yeah, I haven't put like kind of like
Okay, thank you.
bars there for the error. Yeah.
But I think I try to understand what Michael was saying. He was looking for a word like huge impact, correct? I think you articulated very well. This this concept, for many reasons mentioned, could be not just error, could be very biased, correct? I mean, the vast majority of your points are below 5-6 kilometers. Everything above is based on the continuity argument that everything has to go to 0. At 10 meters, probably most of the things go up and down in 10 meters. That's what Sol's animation. But that's interesting. Katie, you have a question?
Yeah, you showed like those histograms of the updrafts and downdrafts, and the numbers are impressive, especially for 20 days of data. Are those like every single scan, or is it every gate? How do you actually get those values that you're putting into your updrafts and downdrafts?
Yeah, I mean, these numbers are high, but I think like what these numbers are is more like once you get your grid, like which point of your grid is labeled as an updraft or a downdraft.
Okay.
So our grid is like 1 kilometer by 1 kilometer, so we get like many points per case, I guess. So that's why these numbers looks kind of like, but a lot of like these updrafts or downdraft are part of the same kind of like maybe a storm or system. So yeah, but that's why they look like, oh yeah. So I think like in total we have like something like 500,000 kind of like grid points, I guess, that were either category as an updraft or downdraft. Yeah.
Were there any limitations on what qualified? Like, did you use the entire volume, or were you only looking at certain elevation angle? Like, how did you actually get your updraft downdraft?
Yeah. So another kind of like yeah, like another area, or we kind of like constrain this analysis only for areas that were classified as a convective cell. So somebody else ran a kind of like a cell tracking algorithm. I guess at PNNL they have this data set to from CSAPR that they found the cells and kind of like they run this kind of like cell tracking data set. So I use the same kind of like algorithm to just identify which part of the radar data is part of a cell, and then I use that as and then extract from there what was the updraft and downdraft. Yeah, but I started from like convective cells, I guess. Yeah. Yeah, thanks.
You guys are very skeptical about updrafts here. Steve?
Yeah, maybe I'm off the wall on this. If I am, just tell me to stop talking.
I will.
It might be helpful to go to like your second to last slide, which had to do with attenuation and differential attenuation.
What's
So-
this one?
Yeah, I think well, maybe the one before this is that one. Yeah.
Okay.
Okay. So my impression is that this attenuation must be related to bright band. Is that correct? Okay, so I'm at least not totally off base here.
No, bright band exactly, but yeah.
So, okay, so why do we have the bright band? We have the bright, correct me again if I'm wrong. We have the bright band because it's water, liquid water, that's responsible for the reflectance. And when you have the melting ice, you've got that liquid water that's in a coherent, within a coherence of your wavelength, is spread out over a much larger dimension because it's melting on the surface of this ice crystal. And so it's a bigger antenna, if you wish, and that's why you get the bright band. So that's my impression. So now what you're doing on your attenuation, I think, is like if we had a beam that's going through a melting zone. So the melting zone gives you a lot more attenuation because of the scattering, much higher scattering per volume, per distance. And then it goes, you're getting scattering from further behind from the normal scattering, and then it has to go through the bright band twice. And so that's the attenuation, I sort of think. Is that more or less correct?
Yeah.
Okay, so far so good. Now my question comes to the differential attenuation coefficient, which to me seems like it must have to do with the orientation of the crystal. That somehow the crystal is more oriented horizontal or more oriented vertical, and that's what's responsible relative to the beam polarization. Then that's what's responsible for the differential absorption coefficient. Is that still more or less we're following you?
Yeah.
Yes?
Yeah.
Okay, good. That part I'm understanding. Now, my question then is on the sign of the differential attenuation coefficient. Are you learning something about the orientation of these crystals? Are they more oriented vertically or horizontally? Can you say that from the sign of the differential attenuation coefficient?
Yeah, that's a good point. I mean, like this study was more like targeting hail, like more than ice, like melting hail. And then the other thing is like the hail is for this particular band, we start having like some resonance at like very close to the size of the hail of the hail, and then yeah, so I think I was doing more like a study on the hail, but that's a good point, I guess.
So it may be more complicated than what I'm thinking about, simply getting that there's a greater probability of vertical or horizontal orientation of the crystal.
Yeah, and also like you have to take into account like the resonant part, so things are not linear anymore when you get into that domain.
I was hoping it was simple, not complicated.
But yeah, no, that's a good point. But yeah, I haven't done this study in the melting layer, which I think also could have like some helpful insights. What's going on?
Yeah, I think there'd be interesting physics to say whether these wet crystals are more oriented vertically or horizontally. That's what I'm trying to get at. Okay, thank you.
Yeah, no, and I conducted also like scattering simulations, so that's another big part of this project is like figuring out like what kind of signals you have and being able like to replicate them on simulations and know what's going on.
I'm less confident in the simulations. I'm more confident in the measurements. Thank you.
Sure. Thank you, Steve. What?
Yes, so about this experimental attenuation coefficient, is it possible to do theoretical calculation of the attenuation coefficient?
Yeah, or I don't know if
it should be right if you have specification of the say the melting ice.
Yeah.
I wonder whether say a comparison would be useful.
Yeah, I think like you can use maybe like a scattering model, and then the thing is like, what do you put in your scattering model? Do you use like, if you use a T matrix? Do you put ice and water and
So the idea would be,
components?
ideally, given this information, you want to retrieve this input data, but in terms of verification, maybe
Yeah,
some idealized distribution.
yeah, yeah. That's another like, yeah, like aspect that I've been working on like simulating melting ice too, and it's yeah, it can be challenging because there you have multiple options, and you don't know, and they give you like really different scattering results, and um, and yeah, and if you want to use, yeah, like it depends on the model. Like you can use maybe like a sphere coated with water, like a sphere ice, and then the sphere ice having a sphere kind of coat of water, and then I try that, and that gives you different results. If you think like it's more like a small particle of ice being in the same coat of water. So yeah,
It's an unconstrained problem.
yeah, I think like it depends what you simulate, I guess.
Yeah.
But yeah, so
You're talking spheres. You showed us some pictures of some ice in one of your slides.
Yeah.
They're anything but spherical.
yeah, you're right. Yeah, yeah.
It's like the book, Consider a Spherical Cow.
Yeah.
Any other remaining questions?
Very simple. This is a clarification question. In the first slides, when you are looking at the Doppler velocity, there was one on the left where it had a simple peak and it's very easy what the velocity is. And then when you have turbulence, kind of spreads the peak.
Yeah.
But
Which slide is this one?
no,
At the beginning.
One of your earliest
yeah,
ones.
the principles.
One more.
Yeah, that
Oh
one.
yeah. Yeah.
So the one on the right is the one with the turbulence, right? So in that particular case, how do you determine the velocity?
Yeah, yeah. This case was probably yeah, challenging because you have like two components, like it's like a positive velocity and a negative velocity, and it could be like basically, well, in the radar measurements, like if you don't do like a spectral analysis, you will only see one number from this spectrum,
Right.
and it normally tends to give like the like either positive or negative to whoever has a higher energy, or when you integrate this.
So it would be very biased.
Yeah, or you miss the negative part.
No, we don't want to give a bad.
Exactly.
Let me elaborate if I allow to. Okay, so that's the Nyquist frequency, correct? So that's folding. You take this part, you move it here. So the peak is actually here. So this is the Nyquist sampling frequency of the radar. If velocity exceeds these hertz, okay, then they're folding back.
It's
like-
rose.
Yeah, it's like
I thought
in the
it-
movies you see the spinning wheels going the opposite direction is the number of the frames on the video, correct?
Oh,
So the
I
radar
thought-
is not sampling enough to see something goes very fast. So you reverse, as you reverse the spinning wheels in the movies, there you go to from more positive hertz to negative hertz. A sampling thing, correct? So effectively, the first to do the radar does takes this part, moves it here, the peak becomes one peak. It's more noisy than this one, but the velocity is here. So the radar typically there are two ways to do it. If it does an autocorrelation function, always get the mean right. Doesn't matter if it is split. Or if you do an FFT Fourier, first you have to fold this there, you get it still right. You're still gonna get it right. Okay, so there are techniques to get it right. This is not a bad case because this part belongs actually here.
I thought because being turbulent, then you have a lot of random walk, so you don't have a specific peak. That's
Yeah.
how I was approaching it.
Yeah, turbulence, the first thing we do, we just make that thing broader. If in the same volume we have an up and a down, we're gonna split it, half of it going up and down. So this extreme is an extreme case that was a real.
Yes.
But because this is so close to the cutoff, this effectively piece you can imagine that was here actually. Just because of folding move there, not that you have volume going up and volume going down. This can happen, very rarely, that big of split. This is an artificial split because of the way that the radar samples. This part belongs actually.
Okay.
I was gonna interpret that as a frequency distribution of velocity along the vector of the beam, no?
All right, let's go have pizza and I will tell you all about that. So, no problem. So this is the distribution of velocities, but cannot be seen. You can see that there actually is a distribution just because of the way you sample, correct? So it's just an artifact here. This is an artifact at this point.
Because of the rate or something.
Yes, yes.
Let me ask the speaker, is that a frequency distribution of velocity along the beam?
Yeah, like the way it is.
Yeah, but the negatives are focused
Like,
I'm asking the speaker.
yeah, like the way it is, like this peak is pretty close to the Cardian energy. It could be like this is just folded and spotted here. But as Paul was mentioning, it could be there are instances too where things can move at different velocity and you have multi-modalities, and those are really interesting to study too, like when you have, because you have real kind of like things kind of colliding in the same volume. So
Well, it's both motion. These particles are traveling with the air.
Yeah, but I think Pavlos is right in the sense that what we are looking at is the Doppler frequency. It's not the distribution of velocity.
We have addressed it the last 30 years. Okay, we can do that.
I think like the thing with the spectrum is like it's periodical, right? Like actually like this spectrum will repeat here, kind of like yeah, and when you have particles that are moving faster than what you can scan actually, then you start having like unfolding too, and then detecting what is actually like fold, like velocity and actually like real velocities is also.
It's velocity along the beam direction. It's not vertical.
Mm-hmm. Yeah, but I guess like when if things are moving faster than what the radar can catch, then I guess this portion of the spectrum will move to the negative part.
Okay, that's a mechanical limitation, but in principle, within the volume that's doing the scatter, that covers a fair amount of real estate. You've got small parcels moving towards you and small parcels moving away from you. And that's why you get a spread. No?
Yeah, if you have things like a vertical like shear, like very strong shear, that could happen. Like when
Yes.
like you can start having like things kind of like moving at a different velocity.
Yeah, I don't, it's mechanical effect if your radar can't keep up with it, but I don't care. But I'm interested in the physics.
Well, it's part of the measurements, like to understand, like what's the radar is observing, then start making sense of the physics.
You got small parcels within your scattered volume. I think that's what that represents.
Very good. Let's thank the speaker one more time.
Yeah.